Acid-base properties of salts. Well, salts are a special class of compounds. They're ionic, so they are charged particles and they ionize, and they break up into ions, and those ions can behave as acids or bases. So the salt of a strong acid and a strong base gives a neutral solution. This is the most common example we did in intro. So you had a strong acid and a strong base, and you get a neutral pH of 7 for this salt. Here are two examples of a neutral salt: potassium chloride and sodium nitrate. Now, I talk about this a little bit differently than the textbook. I never have problems figuring out if a salt is going to be acidic or basic. We'll go through what the book is talking about, but I'm going to show you a little trick right now to help you figure out if the salt is acidic, basic, or neutral. So, for example, KCl is a neutral salt. How do I know that? Well, before it was KCl, it came from the base, KOH, and HCl. Now you'll notice the potassium hydroxide, which then would react with HCl, would give KCl as a product, is a strong base. And HCl is a strong acid. And a strong acid and a strong base, which ionize 100%, are going to form a neutral solution. So too with this one, we have NaOH and HNO3, both strong. NaOH strong base, HNO3 strong acid. It's going to produce a neutral salt. The positive ion of the salt always comes from the base, and the negative comes from the acid. I almost think about it like the parents to the salt. In other words, with NaOH, NaNO3 is the child, NaOH is, let's say, the mother, and HNO3 is the father. And so the parents of NaOH, if both of those things that produced it were strong, acids and bases, then this salt will be neutral. A basic solution is formed if the anion of the salt is the conjugate base of a weak acid. This is the way the book will talk about it. So for example, NaF and KC2H3O2. Now what they say is exactly true, but if we use my trick, NaF comes from NaOH, which is a strong base, and HF, which is a weak acid. Well, think about a strong base and a weak acid. Which is more powerful? Obviously the base. So the overall answer is this is going to be a base. Sodium fluoride is going to be a base. K, or potassium acetate, came from KOH, which is a strong base. C2H3O2 comes from acetic acid, which is a weak acid. And again, putting those two things together, we're going to get a base, because the base overpowers the acid. Or, as your book says, a basic solution is formed if the anion of the salt is the conjugate base of a weak acid. And they also say Kw is Ka times Kb, and of course, I'm going to erase. You're going to use Kb when starting with a base, which makes sense. Acidic solution is formed if the cation of the salt is the conjugate acid of a weak base. Again, let's look at this example, NH4Cl. The two components were what had to be mixed prior to producing ammonium chloride, of course, is NH4OH, which is a weak base, and HCl, which is a strong acid. Well, again, strong acid and weak base come together, and the result is going to be acidic. So ammonium chloride is going to be acidic. Again, they're showing you about Kw, and we're going to use the Ka when starting with acid. So in general, if the cation is neutral and the anion is neutral, then your solution is going to be, your salt is going to be neutral. If the cation is neutral and the anion conjugate base of a weak acid, it's going to be basic. So here are some other examples, going through using your book's terms to understand if something is acidic or is it basic. Now, the last one using my method, aluminum sulfate, aluminum comes from AlOH3, and this comes from H2SO4. So if both of them are weak, then you're going to have to figure out if which is more important, the Ka or the Kb value. So in general, here's a chart about predicting the pH of salt solutions from weak parents. Interesting, they're using that here now. So if the Ka is greater than the Kb, obviously the acid is more important, and therefore it's going to have a low pH. If Kb is bigger than Ka, then it's going to be more basic, and if Ka equals Kb, it's going to be a neutral solution. So strong. So here's an example where they're giving you two weak acids, the Ka, first one being 1.8 times 10 to the negative 5, and the second one 6.2 times 10 to the negative 10. Calculate the Kb values for their conjugates. Well, pretty easy, because Kb times Ka equals Kw. So all you really need to do is you need to take these numbers here, like for this one. To get this one, you're going to say 1 times 10 to the negative 14 and divide it by 1.8 times 10 to the negative 5. And you're going to get that number. And you would do the same for HCN. Alright, arrange the following 1 molar solutions from lowest to highest pH. Wow, there's a lot of them there. Alright, so I'm going to look around and I'm going to try to break it up, and I'm going to see which ones are acids and which ones are bases. Now, obviously the lowest pH is going to be the most acidic. So I'm going to look around. Alright, HBr I know is a strong acid. And NaCN is a salt. NaCl is a salt. I also know that has a pH of 7. NaOH is a strong base. This is a weak base. HF is a weak acid. Ammonium chloride is a salt. And HCN is a weak acid. Alright. So now we have to go from the lowest to the highest pH. Well, the lowest pH is going to be my strong acid. So that's going to be HBr. So I'm going to stick it way over on the left, because I know that's going to be the weakest. So goodbye to that. Strong base is only one, which is NaOH. So I'm going to stick it way over on the right. And let's see what else we have. We have a weak base. I see that. That should come next on this side. Then I have some salts, which are going to be in the middle. And then I have some acids. Now we have to know about these acids. I happen to know that HF is a stronger acid than HCN. You'd have to look up the Ka values. So I'm going to put HF and HCN in order. And then we're left with these 3 salts. Now some salts, of course, have a neutral pH like this one. So I already know that's going to be the middle. The question is, what about NaCN and NH4Cl? Well, NH4Cl comes from NH4OH, which is a weak base, and this comes from a strong acid. So this thing is acidic. NaCN comes from NaOH, which is a strong base, and HCN, which is a weak acid. So this is basic. So therefore, moving backwards this way, I'm going to put NaCN here. NaCl is going to be in the middle, and NH4Cl is going to be the acidic, so it's going to go more towards the acidic side. So this is more acidic, and this is more basic. It's going to have a low pH on the left and a high pH on the right. Let's see if we're right. Oh, and justify your answer. Okay, well I did that along the way. Let's check it out. HBr, check. HF, HCN, NH4Cl, NaCl, NaCN, NH3, NaOH. Yay! There we go. That's how you do it. So let's look at a question, maybe that's a little bit different than this. Consider a 0.3 molar solution of NaF. The Ka for HF is 7.2 times 10 to the negative 4. What are the major species? In other words, what are the things that are going to be the major contributor of pH? Well, remember, salts ionize. So we have Na positive, F negative, and water. And we're going to think about, why isn't NaF considered a major species? Well, remember, if it breaks apart into ions, well, then it's not a major species. So that's why it's not here. So what are the possibilities for the dominant reactions? They are the following. We have the fluoride ion and water. We have, self-ionization of water for number 2. Sodium ions could combine with water, or sodium could combine with fluorine to form sodium fluoride. Which one is it here? Is it going to be the fluorine with water to form HF, or water combining with water, or the self-ionization of water? We have to look at which is the bigger Ka or Kb value. So we're going to determine the equilibrium constant for each reaction. And I don't think they showed you that, which isn't very helpful. Let's see. So I guess you have to look up the values. That's just information. I think in the next example, we're actually going to do some solving. So I'm just going to keep going ahead. So calculate the pH of a 0.75 molar aqueous solution of NaCN. And the Ka for HCN is 6.2 times 10 to the negative 10. Now, we can think about the major species of NaCN. And you might say, well, why are they giving me this if they're giving me this? What's that about? Well, NaCN, when it breaks apart, is Na and Cn, and you have to, and of course water, it's an aqueous solution. So you have to figure out which one is going to be the major contributor of the pH here. And you might say, well, it's probably something with Cn, because you'll notice they give you HCN down here. So that's a big clue as to which one's going to be the major species. If they only give you one Ka value, and you're going to have to use it, it's probably the one that contains that ion. So that's the first hint. And then what we have to do is we have to show Cn negative reacting with water, acting like, in this case, what is it acting like? An acid or a base? Well, I see it says Ka here, so part of me really wants to have it acting like an acid, but it's going to be really difficult to have Cn negative release a hydrogen, because guess what? It doesn't have any. So therefore, the only thing I can really do is make it act like a base. And that would give me HCN and OH negative, which is fine. We can do that. And if we do that, well, we're going to figure out the pH. All right, so let's look at how to do that. Ice. And we have a 0.75 molar solution. 0.75. And we don't have any products. So, just like before, minus x plus x plus x, 0.75 minus x. So we're ready to do the old equilibrium, 0.75. But this time, you'll notice we are producing OH negative. We are not producing hydrogen ions. So even though they tell me right here that the Ka for HCN is 6.2 times 10 to the negative 10, that's not so helpful because I can't use that number. I actually have to use Kw to figure out the Kb value for this reaction and then put it here. And when I do, I'm going to use my calculator to do it. 1 times 10 to the negative 14 divided by 6.2 times 10 to the negative 10. I get 1.61 times 10 to the negative 5. So that's the Kb value. Then I can solve by multiplying by 0.75, and let's see, 5, and I get 1.2 times 10, 1.20 times 10 to the negative 5, and then I'm going to take the square root, and it looks like I get about 0.0035. That's x. 0.0035 molar. That's x value. Alright, then I want to calculate the pH of this. What do? Well, that's the concentration of OH. So I'm probably going to take negative log of that. 0.0035. And when I get about 2.46 or so. So pOH is 2.46. So I need the pH. So I'm going to say 14 minus 2.46, and I get 11.54. So that should be the pH. Now, I think this particular program, this PowerPoint, is going to show us the book's way to solve this. Let's see how they did it. And they want you to stop and think about it. What are the major species? And that's what we did. Of course, we got that NaCN and H2O. And of course we know NaCN is not a major species because it ionizes and it breaks apart, as all salts do. What are all possibilities for the dominant reaction? Well, let's see what they say they are. There are 4 of them. And you can see there's CN. In fact, that's the one I used, number 1. You could also have water. Na is going to form NaOH, which is not going to happen because it's a strong base, and of course the reformation of the salt, which is not going to happen either. And we know which one really occurs. So how do we decide which controls the pH? It's all about the Ka value. Now the Ka value on the previous slide was bigger than 1 times 10 to the negative 14, and that's why this is the major contributor of the pH. So let's see what they do. Oh, look at that. Had I just pushed the enter button, we would have gotten here a little faster. But hopefully you understand it now that I talked you through it. So we're going to set up an ice chart. There the numbers are like we had before. And we have to get the Kb value, remember, because we have OH negative. So I got 1.6 times 10 to the negative 5. I might have used a few more sig figs, but that's the idea. And in the end, I got about the same thing, 11.54. So that's how you solve using information about salts.